They just factor the bottom 4. Now, theoretically, is that hard or easy to factor? What do you think?
It's easy.
It's not bad. It's not bad. It's not bad. It's pretty straightforward. It could be a lot worse. Technically, it is a cubic, but could the cubic be a lot worse? Yes, could be a lot worse. Okay, so you need to solve for A, B, and C. How are we going to solve for A, B, and C?
We're going to factor out.
Make them the same.
We're going to make a common denominator. We're going to. So we have. What do we have here? We want 1 over x cubed minus x squared to equal A over x plus B over x squared plus C over x minus 1.
Yep.
We multiply by the common denominator, and what do we end up with? 1 equals A times x squared times x minus 1 plus B times x minus 1 plus C times x squared. I did the math out of my head and wrote the wrong thing.
Should be AX times x minus 1.
A times what?
It should be AX times x minus 1.
No, it's A times these two, right? And then B times x minus 1. I think this is right.
But the common denominator is x squared x minus 1.
Oh, did I multiply by too much?
Yeah.
It's not wrong, but did I multiply by too much? Yeah, okay. So can we make it a little simpler? We don't need to make it worse than it is. You're absolutely right. So the common denominator is going to be
X squared x minus 1.
x squared x minus 1? Okay. I see what you're saying. Okay. So we're going to multiply everything by x squared times x minus 1. Okay, so it's going to be x times x minus 1. I see what you're saying. Plus b times. Is this a little nicer?
Yeah, much nicer.
Yeah, it's a lot nicer. Fine, you're right. It's not that bad. Okay, so what should we do now? What tack did you guys take to attack this? What do you think, James?
X is 0.
You just took x is 0?
Yeah.
Sure. So if you did x is 0 as your magic number there, it kind of helps you out a little bit because then you end up with 1 is equal to b times. So b is equal to?
Next one.
Yay. So then what do you do next?
You plug that in.
You plug that in. You plug b equals 1 into this?
No, yeah.
Into there? Okay. You can, sure. Or what could you do? Any other ideas for what you could do? Hold on. Pause. That's totally valid.
Yeah,
I'm not saying it's wrong.
Yeah, x equals 1.
How about x equals 1? If we're going to do x equals 0, why don't we just do x equals 1? What do we end up with that? We end up with 1 is equal to cx, well, c times, well, 1 squared, right? So, hey, oh, look at that. That's nice. Now, what should we do with b and c? Plug them in, yeah. So 1 is equal to a times x minus 1 plus negative 1 times x minus 1 plus 1 times x squared. And now it's a matter of doing what? Hoping it works, right? What do we have to do now? Expand. Yeah, we actually have to do it out. And we just hope there's no contradiction, right? Are we wary of contradictions?
Yes.
Especially since theoretically, are these numbers 0 and 1 in the original domain of the function? No. So we just need to be careful because there is an alternate path we could take. We could do it out and correlate the coefficients, which is what the book really likes you to do because it's a much more solid way. Yes, James.
So I kind of did all of them.
So theoretically, what does this come out to be? A times x squared minus x minus what? Minus x plus 1 plus. It's looking, no warning, too many warning bells are going up right now. What do we end up with here? Minus x plus 1 plus x squared. What do we need to combine? We need to combine what? Like terms? Equals, how many x squareds do we have? A plus 1 x squared, right? That takes care of that one and that one, right? Minus a plus 1 x plus 1. Does it work?
Yes.
It does work. In both cases, this a must be negative 1 here, right?
Yes.
But also a must be negative 1 right here. So we avoided a contradiction. Is that kind of cool?
Yeah.
So if you can dance around and kind of use this method, sure. But what happens if we ran into a contradiction here? We would have to go back and use which method? Correlating coefficients. I don't think it's labeled that way, but I think that's accurate. You're correlating the coefficients and setting up your simultaneous equations. Did this end up working? Sure. We're not done yet, though. What would we need to do next? We're trying now. What are we integrating? A is what? Negative 1 over x plus negative 1 over x squared plus 1 over x minus 1 dx. Are you guys okay with integrating that?
Yeah.
Cool. Yeah, the setup is what you need to focus on. Henry, here's the challenge. You need to rewrite this into something that has pieces that you can attack, and right now it doesn't really have pieces you can attack. So what do you have to do? And it tells you, use division. So just please use the thing it tells you to do. So you need to do x squared plus 3x plus 2 divided into x to the fourth plus 3x cubed plus 2x squared plus 1. Can someone tell me, I mean, this is, I did not teach you this. I wasn't around for this. But what do you, theoretically, you need to do something to set yourself up for success here. There's something that you need to write in. Ty.
It's so tempting for me to separate that left part except for 1. Because when you multiply by second x squared, it's going to be the same. So
Oh, I see. It's close. It's close, right? But, okay, when we're doing the division, what do we have to put in?
Plus 0x.
Thank you. Oh, that's so important. If you don't put that in, you tend to get things wrong. You need all of the descending terms. Excellent, excellent point. Excellent point. The only thing you need to remember for dividing for polynomial long division is this phrase: leading over leading. This is what you're doing all day long with polynomial long division. Leading over leading. What's the leading term here?
x to the fourth.
X to the fourth. What's the leading term in this? What's that called? The divisor?
Divisor.
Over what? Oh, it's over x squared. What does that equal? Hey, we just did leading over leading. We got to, oh, you write it over the. And just like regular long division, what do you do with that x squared? What do you do with it? Multiply. So you get x to the fourth plus 3x cubed plus
2x
squared. You subtract, and what do you get?
0.
You get 0. After you do the subtraction, what do you drop down? Oh, you drop down this. Oh, it's 0. Oh, leading over leading. What's oh boy. It's gonna be plus what?
0.
Plus 1.
Is it plus 1?
0.
Oh, no.
It's 0 right now, right? You can put a stutter step in here, that's fine. You multiply this through, you get 0, right? And when you subtract, because you bring down this 1, what do you end up with for a remainder? 1.
Over x squared. Plus
That's the
3x.
remainder. Yeah, exactly. So you had to do the full remainder. It's inaccurately labeled in some books. They call 1 it's in one way you could call that the remainder, but is that really the remainder? No. What we're showing, just to be totally clear here, is we're now showing that x to the fourth plus 3x cubed plus 2x squared plus 1 over x squared plus 3x plus 2. What does that equal? X squared plus 1 over x squared plus 3x plus 2. That's what we just showed. So if those two things are equivalent, you can integrate. Integrating one is the same thing as integrating the other. Hold on a sec. So we are now integrating this expression right here. We're integrating that. Now, that's two integrals. Is the first, oh, we can do the first one. It's going to be x cubed over 3. But what do we need to do to this integral? We need to, it's x plus 2 times x plus 1. Oh, are we set up for a partial fraction now?
Yeah.
Now we can set it up as a pretty straightforward partial fraction. Yes, Henry?
You go back.
So for example, let's say we had x squared plus 2 going into, I don't know, x to the fourth plus 2x cubed plus x squared minus 6x plus 5. So let's say we just had that. It's leading over leading. What's the leading term underneath the radical? X to the fourth. What's the leading term of the divisor? That's going to stay the same. This is equal to x squared. So you line it up with the same power. You then multiply. Each term, you multiply there and you multiply there. So what do you get? X to the fourth plus what? Plus what? 2x squared. And now what do? You subtract that entire thing. And what are you left with after you do the subtraction? 2x cubed minus what? X squared. Now you do leading over leading again. What's the new leading term? 2x cubed. Here's your leading term, everybody. What do you divide that by? The x squared stays the same because it's not changing. It ends up being 2x plus 2x. What do you do with that 2x now?
Multiply that.
Again, you end up with 2x cubed plus 4x. And you then do the same thing again. You subtract. Can someone tell me what you're left with when you do this subtraction? What are you left with? Minus x squared minus. You can bring that down because you need that term. What do you end up with? Minus what?
10x.
10x. You can bring that down again, but you're just looking at the leading, so you don't need to write the whole thing out. What's the new leading term? Minus x squared over, oh, it's the same, equals minus 1. You multiply, you end up with negative x squared minus what? Minus 2. And you subtract, and what are you left with? Negative 10x what?
Plus 7.
Plus 7. You stop here. Can someone tell me why you stop?
The leading term is smaller than the divisor.
What? When you say smaller, what do you mean?
The degree is much.
Correct. The degree here is less than 2. The degree here is less than 2, and that is the degree of your divisor. You stop once you get further. So now, what can you say? You now know that x, what was it? X to the what? Sorry. You now know, I'll write it over here. X to the 4th plus 2x cubed plus x squared minus 6x plus 5 all over x squared plus 2. What does that equal? X squared plus 2x minus 1 plus negative 10x plus 7 over x squared plus 2. How would you check that to see if it's right? Multiply this entire thing by x squared plus 2. That cancels, then you'd have to multiply out the 6 multiplications, and hopefully it simplifies to that right there. Hopefully. Does that help a little bit?
Yeah.
The phrase is leading over leading. Leading over leading over leading. That you just keep on doing that. And what are they asking you to do on this one, Ray? What are they asking you to do on this one? Just to decompose it. They're not asking you to integrate it. They're asking you just to decompose it, which really is what this entire part of this section is on. So what do you have to do, kids?
Factor the bottom.
Yeah, you got to factor this. You got to factor this. And that's probably why you asked about this.
No,
How do you factor this without just looking at it?
Long division.
What do you do?
Long division. That's
There's a
fine.
way.
There is a way. There is a system.
So you separate it into y to the third minus y squared and y plus minus 1. And you take.
Oh, you saw the shortcut. Okay, so yes, I think James is right. You can turn this into y. Hold on. What can you factor out of the first two terms?
Y squared.
This is, yeah, okay, this is, I didn't want it to be easy. We just regroup this. This is called factoring by grouping. I don't like this method. Do you know why?
It's not always working.
It very rarely works. It's the kind of topic they teach you in Algebra 2 or Pre-Calculus where it says, factor this by grouping. Because unless you're specifically told to factor it by grouping, it's so rare that it comes up. I don't like it. Okay, now what does it factor into? Y squared plus 1 times y minus 1. Do you guys want to know the big kid way of factoring this?
Try y minus 1.
Okay, hold on. There's something called the potential rational zeros theorem. Has anybody seen this? Anybody remember this? Ready? I'm not going to write down the general form of the polynomial and do this out with proper notation. I'm going to do it in story form. It's all the potential. It is all the factors of the last term, the constant, over all the factors of the first. The nice thing about this is, what's the constant term? Negative 1. What's the leading coefficient? 1. There's only 2 potential rational zeros. You have plus or minus 1 over plus or minus 1. How many different numbers is that? 1 or negative 1. Those are the only potential rational zeros. If this polynomial has a 0, that's where it crosses the x-axis, it can only occur at 1 or negative 1 if it has a rational 0 at all. Do all polynomials have to have a rational 0? No, they don't. But if they do, they have to fit this. I could prove this. You factor things out in general form, it works. But the point is, you need to test them. How do you test to see if something is a 0? You plug it in. You literally can plug 1 or negative 1 into the original equation and see if there's zeros. What do you find out if you just plug in 1? Well, what's 1 minus 1 plus 1 minus 1? What is it? It's 0. What about negative 1? Negative 1 minus 1. What is it? Negative 1
Plus 1.
Plus 1.
Plus
Minus 1.
Minus 1.
Minus 1.
Minus 1. Minus 1.
Minus 1.
Minus 1. Is that 0?
Nope.
No, but the point is, so now you know that 1 is a 0, but negative 1 isn't. But that doesn't tell you anything about the factoring, right? There's a method for evaluating polynomials that does, as a byproduct of the process, tell you something about the factoring. Do you know what it is?
Y plus some.
Synthetic division. Synthetic division, synthetic
Oh,
division. I love synthetic division. Love it. Synthetic division.
Oh, the 3, 2, 1.
Synthetics. You've watched Blade Runner? Okay. Here it is, right here, kids. This is what we're trying to use synthetic division on, and we'd really like to know what the heck is going on. What synthetic division does, is it actually just evaluates polynomials for you. The first thing you need to do is write out the coefficients of that polynomial in descending order. What are the coefficients?
Plus 1 minus 1.
1, -1, 1, and -1. If there was a space, for example, if this wasn't there, what do you have to put in?
0.
You have to put in 0. The next thing you do, everybody just watch. You put a little bar underneath, and then you figure, what number do you want to test first, 1 or -1?
1.
1. You put it here. I like to circle it to notarize I'm testing that one. The first step, drop the first number down, and you get 1. And then you multiply by this. You repeatedly multiply by this. What's 1 times 1?
1.
Then you add. What do you get?
0.
Then you multiply. What do you get?
0.
Add. What do you get?
1.
Multiply. What do you get?
1.
Add. You get?
0.
You love seeing zeros right there. You love it. It makes you happy because that's the remainder. Not the remainder. That's what it evaluates to. When you plug in 1 into that polynomial, it evaluates to this. The cool thing about synthetic division is that this right here is the remainder. This is the constant. This is the first degree y term, and this is the second degree y term. If 1 is a 0, what factor has to be there? Yeah.
Then it creates a binomial term that is 0, or that is a factor of the
Correct.
original, and those are the coefficients.
So ready? If you know that when you plug in r into a polynomial you get 0, what has to be a factor of that polynomial? X minus r. The name x could change depending on what value you have. But if r is a 0, x minus r has to be a factor of that polynomial. So we now know in this one that 1 is a 0. So what has to be a factor?
1. Oh, that's
Factor must be y minus 1. But here's the cool thing. You see these correlations right here? What else has to be a factor? Y squared plus 1. There's your y squared plus 1. So this right here it tells you that another factor is y squared plus 1. Hey, do you have your two factors? You do. This is cool. Cool stuff. Okay, so far, judging from that setup, that's where you would go. So you tried to correlate the coefficients. 2y is equal to ay minus a plus by squared plus b. What does this tell you? B must be what? 0. Okay, if b is 0, what does this then tell you? A must be 2, but then you have a can't equal 2. So you have a contradiction. Your algebra... Sit up. No, not you. Hey, Ray, you're paying attention. It's the kid behind it. Ray's like, whoa! Sit up straight. Kids, look. So I will tell you that all of the algebra you have done on this is correct. So if all the algebra you have done is correct and you end up with a contradiction, what has to be wrong?
the setup.
The setup. There's something about the setup which you need to modify. Can anybody tell me what I need to modify about the setup?
Remember about a because it's always be 1 degree lower.
The numerator is always going to be 1 degree, and it's the reason. Now I'll tell you this. I kind of set you up to run into this wall, kind of on purpose because I didn't mention this. But the real thing is, we saw denominators. For example, we saw denominators earlier that were like x minus 1 cubed, right? That's a repeated linear term. And you do x minus 1 squared, and x minus 1 cubed. You have to do all of the trailing terms. This right here is not a repeated linear term, but it's not a repeated linear term. It's not linear in the denominator, right? So what do you have to change the numerator to?
ay plus c.
What's the degree of the... Ready? Because it works. Just watch. No. Oh, why? So he asked, did we just really have a who's on first moment there? No, why? Cause y. No, really, it's y. Are we okay now? If you set it up like this, the correlation should work. The correlation should work. Now you're going to prove that you can do it. Put everything away except the pencil. Doing, essentially, is coming up with an equation for the x-coordinate, and we're going to have an equation for the y-coordinate. There's going to be an index variable that's commonly referred to as t. This time is a pretty good index of something changing. What this means is that we get to model movement. We get to model movement on a specific path. How many different ways can a particle move on a path?
2 ways.
An infinite number of ways. For example, can you write a function that models the path of a road? Yes. There's a function that models the path of a road. It might be a polynomial, it might be polar, it might be something fun. Elliptical, cylindrical, whatever, right? How often do cars run into each other, by and large? Not too often, right? 10,000 cars can go over the same road, but they don't run into each other because they are not at the same place at the same time. There are different ways to travel upon the same road. There might be one way to write a function. There are tons and tons, an infinite number of ways to write that same path, traveling on that same path with a parametric equation. There's lots of different ways. But the idea is we are going to have a function for x, and we're going to have a function for y. It tells you what the x-coordinate is, boys, at the back, at a certain time, and it tells you what the y corresponding y-coordinate is at that specific time. So kinds of questions you can answer are like, will these two, the paths will intersect, but will the particles intersect? It adds another dimension to two-dimensionality, which is kind of cool, without going into 3 dimensions. So don't write this down. I just want you to take a look at this. Describe the motion of the particle whose coordinates at time t are x equals cosine t and y equals sine t. Some of you may have seen this. If you wanted to, you could make a table with t, x, and y. How about time 0? At time 0, what's x going to be? What's cosine of 0? 1. What's sine of 0? 0. Oh, what's another good trig value that we could have? How about pi over 4? It's going to be root 2 over 2 and 2. And what about pi over, I don't know? No, we don't need to go that fine. I mean, we can if we want to. It's, okay, fine, we can. But if we do that, we might as well do them in order, right? So if we do them in order, what happens if we have pi over 6? What's x going to be? What's cosine of that going to be? Half. And then root 3 over 2. So I'll do the grid here so you can adequately see. So could you keep on filling this in if you wanted to? So you end up sketching something that starts, well, if time equals 0 is your start, time equals 0, it's here. What's that point? 1, 0. Well, at pi over 4, where is it? Oh, it's right about, we can estimate it. It's right about here. It's going to be root 2 over 2, comma, root 2 over 2. What about pi over 6? Oh, that was right about here. What was that? Root 3 over 2, comma. Oh, did I get that wrong? Is it 1/2? What did I do wrong there? I flipped something around.
I'm still working on that.
Good. That's reassuring. That's good. Okay. So we have root 3 over 2, comma, 1/2. So what do you see? What's going on here?
The horizontal axis is still x.
No, the horizontal axis is still x. That is correct. At time equals 0, this is where the point is. At time equals pi over 6, this is where the point is. At time equals pi over 4, that's where the point is. So could you keep on tracing out points?
Yep.
And what has James already told us? What happens to this thing? It goes around and around and around and around in a circle. So one way to notice that is tracing out points. There's another way to notice that. You can notice it algebraically. If x equals cosine t, what does x squared equal?
Cosine squared.
Oh, if y equals sine t, what's y squared?
Sine squared.
What's that equal?
1.
A 1. What did we just eliminate? We just turned it from a parametric equation into a relation. We eliminated the parametrization of that circle. Now, what did I say before? Can you travel on that circle at different speeds? But are you still in the same circle? Could you start at a different point, theoretically?
No.
Absolutely. So, for example, let's say I said x is equal to cosine of, I don't know, t plus pi. And y is equal to sine of t plus pi. Did the path change? No. Did the speed of this particle change? No. But what changed? Where it started. Where it started changed. Yes, Brendan.
If you did.
Wait, you sure? Wait, x squared equals cosine squared of 3t.
It's gonna move faster.
Oh, it is. It's going to be the same exact thing, except it's going to move faster. Because if you add these two together, you still get x squared plus y squared is equal to 1. Is that an act? Does this equation give you everything you need to know about this? No. You've stripped some of the detail just to the path. You just have the path now. How many different ways can you write this as a parametric equation? As many ways as you want. Exactly. You can start in different places. You can change the speed, but you're on the same path. You're on the same path. Yes.
If it were something like sine 2.
What's y naught?
-1.
-1. But we need to add something t. So something t. Something t. Something t. So does it tell you what time this is right here? Does it tell you what time it is when the particle is at this point, -1? No, it doesn't. How about we just assume it goes from time equals 0 to time equals 1? How far over does it go? How far over does it go? -3. And how far up does it go? 6. When you plug in 0 into this, where are we? 2, -1. When you plug in 1, where are we? Right there. Did it tell us what time it should be? No. So could we change this if we wanted to?
Yes.
As long as the slope is the same, we could change this. We could dilate this however we would like. We could double these, we could triple them. How many different ways can you write the same line parametrically? Infinite number of ways. Infinite number of ways. Okay, you can pack up, everybody. Oh, wait, no, wait.